morning, ma'am. Screen visible? Am I audible?
Yes, sir.
Yes, sir, audible.
Okay. Shall we wait for some more time or we'll start? Yes, ma'am. 23 are there. I think we'll start the presentation. So last class we are discussing about this equation, right? The rate is in terms of the two resistances, right? One is the mass transfer diffusion controlling resistance. This is reaction resistance. Here, when we are deriving it, we are assuming that there is no ash form, right? This is the reaction. A plus B gives R. A is a gas, B is a solid, gives R gas. Here our assumption is no ash form. When there is no ash form, how many resistances will be here? Because there is a gas phase, one resistance will be there. Here, there is a solid phase, there will be one more resistance here. Therefore, your rate expression, when you derive it, you are getting like this. That is, the rate is the sum of the resistances, sum of the individual resistances of the gas phase and the reaction phase. For suppose, if I assume there is ash which is being formed, if there is ash which is being formed, then what will happen? Surrounding now you see here, this is the solid, this is the gas. So this is the gas and this is the solid. This is the solid surface. We are assuming there is no ash form. So this solid is becoming pores or something like that. But there is no ash which is being formed. For suppose, if there is ash formed, then what will happen is, this is the solid, this is the gas, this is the solid. So this is the outer core of the solid. and as it reacts, the core gets small. This is the inner core, and here there will be some ash form. If you are not removing the ash will be formed surrounding the reaction core, wherever it is. So initially the core is here. As the reaction happens, the core shifts to inner. Am I right? Because that is, you can assume it is coal burning. So when you are burning the coal, the ash is left and the coal, unreacted core is at the center, right? So this particular thing is called as ash. So when the ash is formed and when you are not removing that ash, then the gas is having one resistance in the gas phase, and then there is one more resistance on the solid, because here there is no solid at all because it is converted. It is only ash is there. Therefore, the gas should penetrate through this ash also, then only go to the surface of the solid. Therefore, there will be one more resistance, that is gas resistance first, gas film resistance, then ash resistance, and third one is the reaction resistance. So remember, when there is a ash which is being formed, you get three resistance. If there are two phases, one is the gas film resistance, ash resistance, and reaction resistance. So if you are writing the rate for it, then can you tell how it will be? If there is no gas film, you are getting like this. Am I right? If there is no gas film, we are getting the sum of the individual resistance of the gas film. This is the reaction. When there is ash which is being formed, then you get one more resistance, that is nothing but a ash film. Ash resistance also will be added. This denominator will have three terms, that is 1 by kg plus 1 by k star plus 1 by ash. So 1 by ash. So this should be multiplied into CH. So this tells you how many resistances are involved. You can assume this is more, therefore this will be kg is more, therefore you can neglect this, or you can assume that ash is more, therefore you can neglect it. So based on, you can do simplifications. Instead of here two steps, we get the third step also, that is the ash. Understand? So that is the that is how you will write the rate. Now we got minus RA is K into CA. This is for homogeneous reaction, and minus RA is K dash some K. This entire thing, let it be K dash into CA. This is rate we are writing in terms of K dash or K. Here it is only a temperature dependent term or kinetic dependent term. Therefore, the rate whatever you are getting is called as intrinsic rate. Intrinsic rate. So whatever rate till now we studied in CRE1 is called as intrinsic rate, because you are getting only the kinetic, you are not bothered about the physical properties, physical nature of the reactants, only the kinetic component you are keeping into mind to derive this particular thing. But what K you are getting from here, this rate is called as global rate or observed rate, global rate or observed rate, right? Otherwise we call it as overall rate. In some books, if you see, it is called as apparent rate. APPARANT. Apparent rate. So these are the four names which you get. Intrinsic rate is nothing but only the kinetic, no physical components is involved. whereas the rate which you are getting, including the physical, that is how the solid is porous or solid is not there, or even ash is formed or ash is not formed, all whatever. So here you are not only the kinetic term, that is chemical thing, you are bothered about the physical nature. Therefore, that rate is called as global rate or observed rate or overall rate or apparent rate. So this is important 2 marks question. What is intrinsic rate and what is global rate? The difference between that. Intrinsic rate, you are not bothered about the physical properties, whether the solid is present or solid is porous or whatever it is. So there is no mass transfer effect here. There is no mass transfer effect here. But when you are writing K star like this, you are taking into picture the diffusion resistance or mass transfer resistance of different phases. That a particular rate, when you involve the mass transfer resistance, it is called as this, otherwise called as mass transfer effects will be taken into consideration. Then that particular rate is called as global rate or absorbed rate or overall rate of a reaction or apparent rate. Generally, in our CRE2, we want this rate, global rate or overall rate. We don't want intrinsic rate. So what we do in CRE2 is, to get this global rate, we write your steps as a series of intrinsic rates. Then we will join together or equate them to give you the unknown compositions. That is what we did just now. Here we want the global rate. We want the global rate. So global rate, to get it, including the mass transfer into picture. So we are dividing this particular thing into a series of steps and assuming that each step is an intrinsic rate. Intrinsic rate in the sense there is no only one particular resistance with be there. There is not much of the other resistances. So you are making as a series of intrinsic rates. Then you are writing in terms of intrinsic rates. Then what you are doing, you are assuming an assumption that the steps are in series at a steady state. All the intrinsic rates will be equal. You are making that assumption to give you the unknown, that is CAS. CAS is the unknown, that is the concentration of a gas on the solid surface. Therefore, you are getting CAS in terms of the known quantities. CAS is unknown. CAG we know because bulk concentration, initially what is the concentration of the gas we know. We know what is the gas coefficient, that is mass transfer coefficient. We know what is the reaction coefficient. All that we know. So CAS is unknown. Then you can substitute this CAS in this equation to give you the global rate or absorbed rate or apparent rate or overall rate. So if you see here, your apparent rate will be a combination of the resistances into the CAG. CAG is nothing but the gas film resistance. So here important thing is intrinsic rates and global rate. Intrinsic rate, to find the global rate in CRE2, because you are having heterogeneous systems, to get that global rate to get it is very difficult. So what you are trying to do is, you are splitting this entire equation as a series of intrinsic steps or intrinsic rates. Then you are equating that intrinsic rates to give you the overall global rate. Yeah, I stop. Any doubt, Mike, here? Yeah, any doubt? 48 people. You understood what I mean to tell? What is intrinsic rate and global rate, right? So in CRE2, we always talk about global rate. Till now, in intrinsic rate, I didn't even tell in CRE1. Only now I am talking. The whatever rate we calculated in CRE1 is intrinsic rate. There is no mass transfer into coming into picture at all. Only the kinetic term we discussed. Shall I go for the next thing? Shall I go for the next one?
Yes, sir. Yes, sir.
So remember that, right? So this very important. This difference you should know: intrinsic rate and global rate. Now, can anyone tell me whether intrinsic rate will be higher or global rate will be higher? Now you calculated the rate.
So intrinsic should be higher, sir,
Why?
because we are considering some resistances in the overall rate. So gradually the rate should reduce, no, sir?
Yeah, very good, very good. So remember that always whenever you are taking a kinetic term into picture, without any mass transfer effect, your rate will be much higher. But generally, if there is a mass transfer coming into picture, your rate will reduce. How much the rate is being reduced, that is what we give in terms of Thiele's modulus. That we'll see in the next lectures, not now. So your rates will always be less than your intrinsic rate. How much this mass transfer is affecting the rate, that is what is one dimensionless number we will give. That is the Thiele's modulus. Okay. So due to the mass transfer, how much rate is being reduced, right? That we'll see a bit later. So now you understood what is intrinsic rate and global rate. So remember that intrinsic rate, there is no mass transfer. When there is a mass transfer into picture along with the reaction, then there will be a global rate, observed rate, overall rate, or apparent rate. So different books will give you different rates. This every book will give you the same intrinsic rate, but global. Some books will give you global rate, some books will give you observed rate, some books will give you overall rate. In if you see Smith or James Smith or some other book, he will give you in terms of apparent rate. So all the four is the same. Okay. So let us go to the next slides. Now we understood this, how to reduce to whatever we want, right? So last class we are discussing about this contracting patterns. It can go either in terms of a plug flow or mixed flow. We know that plug flow there is no there is no what do you call mixing, whereas in mixed flow there is a mixing. When there is a mixing, then the fluid can be a micro or a macro. Micro in the sense everywhere the concentration is same, macro in the sense different lumps of the particles will have different concentrations. So when there is a mixing, you should understand whether that particular thing is going as a micro mixing or macro mixing. Based on that, your conversion will change. So in real process, these are the ideal contracting patterns. In real patterns, it will follow any one of these five. Five can be both A and B is plug flow. It can go as a counter current or a co-current or cross current, that is perpendicular. Or one fluid can go, or one reactant can go as a plug flow, the other reactant can go as a mixed flow. Either this is plug or this is mixed, or this is plug or this is mixed. Both is going to be the same phase, same thing. Two cases, that's what he is giving you. Plug A, mixed B, or plug B, mixed A. So two cases will come here. Both will be the same. Or you can have one more, that is mixed A or mixed B. Am I right? So both can be a mixed. Right? Both can be mixed in the sense, again, in mixing, one can be a micro mixing or other can be a macro mixing, or this can be a micro mixing or this can be a macro mixing. So again, two cases will come here. So overall 3 plus 2 plus 2, total 7 cases will come. Am I right? So each one of it will have different conversion and different design expression which you need to take. For this kind of things, you need to take a plug flow expression, and for this kind of things, we need to take a mixed expression. Again, when you are taking a mixed expression, you have to know on what phase you are trying to write, whether you are trying to find out the conversion of A or conversion of B. If you are trying to find the conversion of B, then you have to B is in a mixed flow. Therefore, you have to take a mixed flow expression, taking into picture of micro or macro mixing into the picture. Okay. So that's all about the what do you call the introduction part, or telling about rate controlling step, or whatever you name for the rate equations for the heterogeneous reactions. We'll go ahead with the next one. We'll go ahead with the next one. Adsorption, because we this is what is coming into picture here. What is adsorption and all, right? So before that, just some 5 minutes break I'll take. I'll just come back. Yeah, sorry. We'll continue. So we are discussing about this two-phase contacting patterns. So when there are two reactants, the two reactants can go as a plug flow. If it is both are going in a plug flow, it can go as a co-current or counter current or a cross current, or it can one can be a mixed and other can be a plug flow, or both can be a mixed or flow. Okay. So let us go ahead with the next one, that is adsorption isotherms. Because when there is a solid involved, what we are assuming here is a gas is transported from the bulk phase to the solid phase. Then there will be a surface reaction at A and B, and the product is being transported back. So in that process, what actually happening is the gas is going and sitting on the surface of the solid. So the gas is being absorbed on the surface of the solid. So how it is getting absorbed, in the sense that we are assuming that the solid will have some active sites. Therefore, this gas is going and sitting on the active side to get the reaction. Then once the product is formed, the product will be desorbed from the solid surface. That is what we assume. So in that process, we need to understand about more about the adsorption now. So what is this adsorption? So adsorption will be given in terms of adsorption isotherms. There are two types of adsorption. One is physical adsorption. The second one is chemical adsorption. This already might have studied in what do you call this physical chemistry. So adsorption is a surface phenomena. Why we call it a surface phenomena? Because the gas is adsorbed on the surface of the solid. So surface of the solid is outer, so not at the inner, right? So that is why it is called as a surface phenomena. So when it is getting adsorbed, there can be a physical adsorption or a chemical adsorption. Now, what is physical adsorption? Physical adsorption is called as physisorption. This is because of the weak van der Waals forces. So the surface area, the pore size distribution in porous catalyst can be calculated using the physical adsorption. So due to the weak van der Waals forces, the gas is being adsorbed on the vacant active site on the solid. It can be reversed. That is, you can take it out. Whereas chemical adsorption or chemisorption, this is formed because of the covalent bonding. There will be some reaction which is going to happen. So activated, this again, it is subdivided into two types. One is activated chemisorption or non-activated chemisorption. Generally, activated chemisorption is a very slow process. Non-activated chemisorption is a rapid process. So what is this activated chemisorption? The rate of adsorption varies with the temperature according to a finite activation energy in the Arrhenius equation. EA is called as the activation energy. The rate of adsorption varies with temperature, because as the temperature increases, your rate will increase, because T is proportional to activation. T is sorry, K is equal to K naught into E power E by RT. As T increases, your rate of a reaction will increase exponentially. So that type of adsorption, chemical adsorption, is called as activated chemisorption, which can be very slow. The other one is non-activated chemisorption, which is very rapid. Generally, this chemisorption occurs very rapidly, suggesting, suggesting an EA as near zero. So activation energy is very less for this kind of thing. Therefore, activation energy less in the sense the reaction becomes faster because it gets activated immediately. Whereas here, as the temperature increases, it has to reach a certain temperature. Then only the reaction starts activating, because it has to attain that activation energy. Then only the reaction will take place. Therefore, activated chemisorption is a slow process. Non-activated chemisorption is a rapid process. So in a rapid process, generally the activation energy will be zero here. Right? So we'll discuss the differences between that. Already you might have studied in the previous semesters. Just a recap of it. So difference between physisorption and chemisorption. You know what is adsorption, right? Adsorption is a surface phenomena. So you are adsorbing, you are trying to remove some solute from the solution by using a solid adsorbent. So the solid which you are going to use on the solid, that is called as the adsorbent. That is the adsorbent. What is going to be adsorbed on the adsorbent is called as adsorbate, the solute, whatever you are going to remove, right? So remember that. So adsorbent in physisorption, generally all solids. In chemisorption, only some solids. Adsorbate is the thing what you are going to take to remove that or take out that solute. So adsorbate, generally all gas below the critical temperature we can be used as a physisorption. some chemically reactive gases only will be selected as a adsorbent in chemisorption. The sorry, the temperature range, physis option is low temperature, here is very high temperature. This one more important parameter, the heat of adsorption, the heat which is getting evolved or whatever you call. Generally in a physis option is very low, whereas chemisorption is very high. The rate, that is activation energy, the rate will be very rapid here because of the low activation energy. So here in chemisorption there are two. It gets activated because of a very high EA or non-activated very low EA. One more important thing is the coverage. This is a very important parameter. The coverage. Coverage generally physis option is multi-layer, chemisorption is monolayer. What is this multi-layer and monolayer? Multi-layer or monolayer is nothing but I'll just draw here. Now this is the solid. Now this is the solid. If the gas is present in the entire on the surface of the solid, that is, it is covering the entire what do you call surface of the solid, then it is called as a monolayer. If the gas is covering like this, that is, this is one layer, above that layer one more layer, above that layer one more layer, then we call it as multi-layer, right? So that's the difference. So this is a very important property, this property and this property. You have to write when they give differences. Rest of the thing, whatever you want, you write. But these three at least, or even the reversibility also. These four parameters you have to mention. One is the temperature range, the other one is the heat of adsorption, the other one is coverage, the other one is the reversibility. The coverage for physis option is multi-layer in the sense like this. Generally chemisorption is a monolayer. So when it is here, one important thing I like to mention, when it is going in a monolayer, this entire thing is called as a monolayer coverage. Generally, this is given in terms of VM, that is the monolayer coverage, volume of the monolayer coverage. The concentration on that will be generally given in terms of Cm, right? So M indicates the monolayer, right? This will come in the later slides. That is why I mentioning here itself. Then the importance of physis option, it is used to measure, determine the surface area or pore size. Chemisorption is used to determine the active center area or the surface reaction kinetics. That we will see. So these are very important differences between the chemisorption and physis option. Generally 2 marks will come, or they can ask you to write a short note on it. So based on one's adsorption, generally adsorption will be given in terms of isotherms. So Langmuir isotherm is very popular. You might have already discussed that. So in Langmuir isotherm, you make some assumption that monolayer coverage of the solid particles. So I told what is the monolayer coverage. So you will assume this, but generally it will be multi-layer. Even though there is a multi-layer, it becomes difficult for you to assume. If you assume multi-layer, equations becomes complex. Therefore, you assume it is a monolayer. Again, no interaction between the adsorbate atoms or the molecules. So what you are assuming is which is adsorbed, there is no interaction here. There will be interaction, but to make our equation simple, we assume that there is no interaction. The coverage is independent of the binding energy. The thermodynamic equilibrium of adsorption and desorption are always equal. That is one more assumption you will make. How much is the adsorbent, which is adsorbed, that much it will be desorbed. That is what one more assumption you will make. Based on that assumptions, you get the different adsorption isotherms. This is the Langmuir isotherm. This will come in terms of like this. Freundlich isotherm is this. This is Redlich Peterson isotherm, tooth isotherm, Temkin isotherms. In all the isotherm is nothing but a relation between QE and CE. CE is the equilibrium concentration and Q is how much it is being adsorbed, right? So the relationship between how much it is adsorbed with its equilibrium concentration is called as an isotherm. So when you are writing this QE relationship between QE versus CE, you get different constants. Kf 1 by n is a constant, Qm is a constant, Kn is a constant, Kf, alpha L, beta, these are all constants. So different scientists gave different expressions. Based on that, you will get different coefficients. So Langmuir isotherm will give in terms of Qm and Kl, whereas Freundlich isotherm they'll give in terms of Kf and N, right? So these two are very important. Our rest of the thing is also important. So in all the things, you will get QE versus CE. So QE is KF. So if you want to find out this particular thing, then you can draw a graph between Q versus CE, take log or whatever it is, then this becomes your intercept and 1 by n becomes your slope. So if you draw a graph between QE versus CE, that is what we call it as isotherms. So types of adsorption isotherms, there are different types. There are 5 types here. You can see here. This V adsorbed is the volume of the adsorption. This is based on the x-axis as a partial pressure because you are assuming it is gas is being there. If the gas is containing only one, then you get a pressure. But if the gas is a mixture, then how much of a particular molecule of the gas is exerting some pressure, that it will give in terms of the partial pressures, right? So either you can write in terms of pressure or partial pressures. So V adsorption on the y-axis and P on the x-axis. Generally, this is how the adsorption will go. Initially, the adsorption will increase. How much of the adsorbent which is going to be put on this adsorbent will increase. Then it reaches a stationary, right? So that particular thing is called as VM. VM is nothing but the volume of the monolayer which is covered, right? So generally all isotherm will be like this. All isotherms will be like that, but there can be difference in that isotherm. You can get like this curve. This is we call as a type 2 isotherm. There can be one more isotherm like this. It is goes on increasing. Especially you can see Br2, that is bromium plus silica. This kind of isotherm you get. This is called as the type 3 isotherm. This is the maximum pressure, right? This is the maximum pressure and this is the variable pressure. The pressure should not go more than that particular thing, right? So this P naught. So type 4, you can see there will be no trend at all. So it increases, decreases like that. There type 5, there is a charcoal versus H2O. You can see how it is going to increase on the do, right? So these are the 5 types of isotherms available in the literature. Most of the adsorption will happen here or here. That does not mean that other isotherms types will come. So any one of the 5, if you do an experiment, your data will fit in any one of the 5. So once we discussed about the adsorption isotherms, the types of the adsorption isotherm, and the difference between physisorption and chemisorption. Now it is for us to write the rate of adsorption. How to write the rate of the adsorption, right? So this I'll take a bit later because we need to discuss still more. Then we'll come back here. So let us assume how to write this rate of a reaction, right? How to assume, because we are writing adsorption is there, we have to write the rate of adsorption. we have to write the rate of desorption and we have to write the rate of surface reaction, right? Because there are three steps, right? Here you can see here. Yeah, gas is transported, the surface reaction is happening, and the product is being dissolved. So how to write the rates for all this? That is what we'll be discussing now. It's 11, 9, 11. Yeah, before going to that, let me stop this and come back to some people are having a lot of difficulties in the calculation part of CRE2, that is lab, right? We'll discuss that because a lot of people are sending messages, mails. So I promised that yesterday one boy that today in the first hour I'll talk about that. Let me talk and then finish off that. Huh? Is it fine, ma? Is it fine? So I'll just
Yes,
tell
sir.
how to do the calculation because today or tomorrow you have to submit. So a lot of people are having a lot of doubts. Well, let us finish up that. So this is the first experiment, right? Batch reactor. So we got whatever the values, right? So you know what is V5, you know what is VN4 and all, right? So here, again, I repeat to you, whatever the data set, what I gave, it was taken from different records. So that time the procedure may be different. So sometimes they will be writing 5, sometimes they will be writing 2. So whatever you are taking in the procedure, whatever I put in the procedure, you take that particular quantity, right? So here I put my quantity as 500 of NaOH and 500 of ethyl acetate. Some of your batches, maybe some 7th batch or 8th batch, the record may be previous one where they took 300 and 400. This is 300 and this is 400, right? So based on that, they might have given some particular, values. So read the procedure once. What is the normality which you are taking? Based on that, you take these values. There are some data sets may be using 500, some data sets may be using 300 because from different books we are changing the procedure. So if you see the previous procedure, we are having 400 this, 300 this. So then in that particular process, your VA and VE will change. VA is nothing but 300 and VE is nothing but 400. If you are taking VA as 500 and VE is 300, that is VE is the volume of the ethyl acetate and VA is the volume of the NaOH. NaOH you are taking 500 and ethyl acetate you are taking 500. You have to put 500 and 500. Don't bother about what they are giving in the data set. We want in the data set only this value and this time. Understand? So here is giving you some values, what is VA and VE, that you have to take from your procedure. So now CA naught, we know what is CA. CA we have to calculate initial concentration of A. A is nothing but here in this reaction. Don't get confused, A and B. Yeah, in this particular, some of people are given. A is NaOH, that is what we are taking. Ethyl acetate generally will assume it as B, but here I am making as E so that to differentiate E is ethyl acetate. Okay, you can write B also, that's up to you. So I am trying to calculate what is the initial concentration of Ca. That is, A is nothing but NaOH. So to know that, what I am doing here in the calculation, all calculations are same. One time I'll tell. Ca naught is the initial concentration of NaOH That is nothing but N2. N2 is, what is N2? You can see here. Because N2, you have to standardize the NaOH. How you are standardizing the NaOH? Yeah, standardization of NaOH is done by the standard oxalic acid. Oxalic acid is having N1, that is the normality. V1 is the oxalic acid. This is the volume you are standardizing. How much is the volume? That is the V2, and N2 is the normality of the NaOH, right? So that you are getting from the table 1. That you have to put here. That you have to put here. And VA is the volume of NaOH which you are using. Volume of NaOH which you are using is 500 ml in your procedure. Here again, some people are doing some wrong here. Here people are telling that, thinking that it is VA is how much you how much you what do you call prepared. You can prepare 2 liters, but that 2 liters you are not using. Only how much you are using inside the reactor only you have to put here. Here it is for 500 ml divided by 500 plus 500. Then that is the CA0. Okay. What is CA0? It is nothing but the initial concentration of ethyl acetate. Initial concentration of ethyl acetate is nothing but CES. That is the how much is the concentration of it into VE. VE is nothing but the volume of ethyl acetate. This is the initial normality. Initial this one is CES is 0.1. I think how much you prepared, right? So 0.1 into 500 divided by this. Now what is CA? CA is since these are reacting, the CA0 is getting decreased because the NaOH concentration is getting decreased. At a particular time, you have to calculate what is the concentration of CA. That you are calculating by V3. V3 is nothing but you can see the second one. This is the V3. Yeah, V3 is this, because this is HCl you are standardizing by using NaOH. This is the NaOH which you are using, standard NaOH, and V4 is the concentration of HCl. So how much V3 is being used to standardize this? Because HCl you are using to arrest the reaction. So how much of the HCl is remaining inside the reactor which is unused for arresting it? That is what you are going to calculate here. So that V3 minus V5. V5 is nothing but this. How much is consumed NaOH for this particular thing? So that minus this into N3. N3 is nothing but the concentration of that divided by the volume of the sample. Here again, people are having different thing. What is the volume of the sample? Volume of the sample is nothing but 10. How much you are pipetting out? So in that already 10 ml of HCl may be there, but HCl is used only for arresting the reaction. How much is the reaction volume? That is what you have to take here. It is 10 ml. Yeah. Any doubt? The rest of the thing is same. XA is 1 minus CA by CA0. You calculate CAs for different values of this. Then do CA0 is constant. CA by CA0. M you can calculate. Then substitute in this and then draw a graph between this versus T. T is nothing but different time. You already have different time here. Times. Then the slope you have to get as you have to get a straight line like this. Even though you are having points somewhere, you try to draw a straight line. Those people who submitted their calculation, they tried to what you call join all the points. In that process, you are getting a curve, not a straight line. It should be a straight line. If you are not getting a straight line, draw a straight line passing through maximum points such that some points will lie on the top and some points will lie on the bottom. Don't draw like this curves, right? Don't draw like this curves. Edit. I can how to write something on this? I don't know. Okay, let us not write. Okay, right. The slope will be this. You know what is CA naught, m minus 1. Then you can calculate K. That is what is K. Yeah, any doubt in batch reactor calculations? Yeah.
Sir, I have data set A,
Hmm.
and when doing standardization of NaOH, my titer value came to 10 exactly, sir. I mean,
Okay.
in the data set.
Hmm.
When we tried to do calculate CA naught and CE naught, we
Hmm.
got both as 0.05.
Yeah, if you are assuming this N2 is 0.1 and C is 0.1, then it will be same both. Yeah. Yeah.
Yes, sir. So we
Yeah.
got M is equal to 1, sir. So we
Okay.
couldn't use
Hmm.
that ln 1 minus xa divided by M into ln 1
Okay,
minus
okay,
xa.
okay, 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 okay. Then you take this as a bit less, 0.9 or something like some 9.8 or something like that. Okay.
So we can
You can
take
change.
the
Yeah,
first data value as
yeah,
9.8 mm.
something.
Okay.
Make
Okay,
sure
sir.
that you are not having M is equal to 1. Okay.
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 Okay, sir.
The rest of the thing, any other doubt? Let us go to the second one. That is batch react, semi-batch. Semi-batch also same things will be happening. CA naught, you are using this equation. CE naught, the formula is different because you cannot calculate how much is VE because you are sending through the pipe with the time, right? So in that process, there will be a little change in the formula. Yeah, you can see here. Yeah. CA naught is VE. VE is nothing but this is how you have to calculate this volume of VE. You know the flow rate. Flow rate times time. You know the flow rate here. In your data set, it is given as 5, I think, but actually it is 2 in your procedure, right? So whatever is given in the procedure, you take. This is 2 LPH, that is liters per hour. This is in minute. So time is in minutes, liters per minute. Therefore, you convert this to liters per minute. Then only you get liters. Am I right? If you multiply both, you will get liters. Am I right? This is LPH. You have to convert to minute. Then you multiply both, then you get the volume of the ethyl acetate. That you use here. That's all. Rest of the thing is same. This for some of the data sets, this T is missing. That is where people got confused how to take VE. Correct? Any doubt, ma? So volume of ethyl acetate, you have to calculate from the flow rate. Flow rate is given LPH. Here in the data set is giving 5, but in procedure I gave it as 2 liters per hour. Huh? Where is it? Yeah, 2 liters per hour. So you use whatever is given in the procedure. Don't use whatever is given in the data set, especially this value. In data sets, I think it is given as 5. That time the procedure is 5. So now we change to 2. So you put as 2 LPH, liters per hour. So this is in minutes. So you cannot multiply both. So you change this to minute. Therefore, multiply by 60. You will get a minute. So multiply both, then you will get the volume of the ethyl acetate. That you put V into T is nothing but volume of ethyl acetate. The rest of the calculation is same. Yeah. Even for a plug flow reactor, you will be doing like that. Plug flow whenever there is a flow reactor. Okay. Any doubt, Mike? I hope I cleared your doubts. Now you can do your calculations and submit. Yeah, Sri Vignesh, I think 53 people are there. You take the attendance and send to me. 53. Okay, including me. So 52. Yeah, any other doubt, man? Any other doubt in the calculation part? Because I'm getting a lot of messages through WhatsApp or mails. Read the procedure once, twice, and what value you are taking. Just be sure of what you are using. It is not that whatever I gave you are using. There should be some meaning of what that equation is being used. So try to understand that and then use it, right? Read the procedure. If the procedure value and here whatever value I given, it is same, then it is fine. Otherwise, you can strike it out and write only the procedure value. Okay. Yeah. Any other doubt, man? Shall I close this? Next class we can go with the rest of the. I think some message is coming here. Okay. No doubt. Pavitra. Okay, good. When you, if you are not having any doubt, no problem. Shall I close, man? So already time.
Yes, sir, we can.
Yes, sir.
Tomorrow or in the evening. Do one thing. Evening last hour. If I'm joining late, you do the calculation part. If I'll join, if I join late, then we'll see. Okay, you join it because I'm having some work in the evening. I'll join, but maybe some 10 to 15 minutes late. Don't get panic. You can do your calculation part in the what do you call it, lab, and ask any doubts you have. Okay.
Sir,
Okay.
don't close it, sir. I have to take the attendance.
You are taking still?
Yeah, yes, sir.
Okay. Yeah, take. Yeah, any other Prithvi? I think you doubt got clear. Yesterday you sending some chat or something.
Yes,
Prithvi?
sir. My M was coming as 1, so I
Yeah.
was thinking whether to use some other formula.
Okay. Now it clear your doubt?
Yeah, now makes sense.
Okay. Then any other people are having any doubts? Yeah, regarding the calculation, now you can talk about the record or observation or that CRE lab, right? Pavitra Madesh, yeah, no doubt. Thank you. Then any other? So we'll see that derivation in the next class. Okay. So I'll stop here. I think Sri Vignesh might have taken all the attendance. It's 51. Okay then. Thank you.